All right, so you should be looking at either a screen in front of you or a piece of paper that has Exponent Foldable and Graphic Organizer on top of it, and we're going to fill this out. Okay, so this first space here, a to the 0 power is equal to 1. The opposite is what this means right here. The opposite of a to 0 to the 0 power is -1. So the power of 0 takes the whole thing to a 1. Or if it doesn't have parentheses around this negative, then it's a -1 there. Okay? If you see this, that is equal to 1 because the negative is included in the parentheses here, and it is to the 0 power. And if by some weird chance they give you 0 to the 0 power, 0 to the 0 power is undefined. Okay, so examples here. 10 to the 0 power, 1. 12 to the 0 power plus 3 to the 0 power. This is 1, this is 1, this is 2. 9 times d to the 0 power. This is 9 times 1, which is 9. 32 times x, y, z to the 0 power. All of that stuff in parentheses is 1. Excuse me, so 32 times 1 is 32. A to the -n is equal to 1 over a to the n. So see what is happening here? It was a negative exponent, and then we reciprocated it. And now it's a positive exponent. So find the positive reciprocal, that's the flip, some of you may be more comfortable with, of the negative exponent. So you just send it across the fraction bar line, and that will change the sign on the exponent. 3 to the -1. So make it a positive exponent. Be 1 over, you could write the exponent of 1, but typically we don't. So 1/3 would work. 2 to the -2. Reciprocal of that would be 1 over 2 to the 2nd. And we could evaluate 2 to the 2nd, and that would be 1/4. Both of those answers would be correct there. A to the -3rd. Reciprocal of that would be 1 over a to the 3rd. We could have a over b to the -4th. So the reciprocal of that, we're going to send this negative exponent across the fraction bar line. And then that means everything is the numerator. So a b to the 4th. Or we might have a negative exponent here. Like that. And we don't like to leave it with a negative exponent. So we take this piece, the p, and leave it where it is. It has a positive exponent. But this 3 to the -3rd has a negative exponent, so we're going to send it across the fraction bar line, use the reciprocal of it. So p over 3 to the 3rd, or we could evaluate 3 to the 3rd and say p divided by 27. Both of those would also be correct. A to the m times a to the n is equal to a to the m to the n. Plus. All right, to multiply powers with the same base, we actually are going to end up adding the exponents. All right, so an example here, 5 to the third times 5. The understood exponent right here is 1. Now if I stretched this out, this means 5 times 5 times 5, 5 to the third. Then I have this other 5 that I'm multiplying right here. Now look right here. How many 5s am I actually multiplying? Write it with an exponent. 5 to the fourth power. So the shortcut here is 5 to the third and add the 1, and we get directly to 5 to the fourth. Sometimes they'll give us k to the negative fourth times k to the sixth, so we're multiplying, same bases, must be the same base. So I would add negative 4 and 6, and that would give me a positive exponent here, k to the second, so I don't have to worry about the reciprocal there. Next, we have dividing powers. So when we're dividing powers that have the same base, that's a requisite, that's required. The powers must have the same base. What we can actually do, the shortcut, would be to subtract the exponents. So some examples to go with that would be y to the seventh over y to the fourth divided by y to the fourth. Now if I stretch this out to 7y's divided by 4y's, y divided by y is 1, y divided by y is 1, y divided by y is 1, y divided by y is 1. And what I have left are these 3 y's on top. So y times y in the numerator. And the shortcut for writing that would be y to the third. So that is the y. That is the reason why this works. So y7, whatever the numerator exponent is, minus the denominator exponent, gives us y to the third. Y to the seventh divided by y to the fourth is y to the third. What if we had m to the negative third divided by m to the negative fifth? Well, according to our rule here, our shortcut rule, we would do the negative third minus negative fifth, and then we use our integer rules, and we'll actually end up with m to the second there. Sometimes when you do this, if we had w to the second divided by w to the seventh, we would do the second minus the seventh powers. Notice we do have the same base of a w. And when I subtract this, I'll have w to the negative fifth. And most of the time, your directions will say, write it with a positive exponent, meaning let's get rid of this negative on the exponent. And to do that, as we've already discussed, we're going to reciprocate this and make it 1 over w to the fifth. Next, a power of a power. To find a power of a power, meaning this exponent goes on that base that already has a different exponent. It's a power raised to another power. The shortcut here would be to multiply those exponents. So some examples here. 5 to the third to the fourth. So anytime you say 5 to the third to the fourth, to another power, that's when you're going to multiply those exponents. So the reason why this works, we've got 5 to the third times 5 to the third times 5 to the third times 5 to the third. I repeated that 5 to the third 4 times. Now if I stretch these each out, those 5 to the thirds, how many 5s do I have here that are being multiplied? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's where we get 5 to the 12th. So this is the reasoning why we multiply power raised to another power. So this is 3 times 4. So our final value here is 5 to the 12th power. What if we had y, and y's to the negative third to the negative sixth? According to our rule, we'll do negative third times negative 6, and that will be y to the 18th power. Here's a fun one. P to the 0 power to the 5th power. Personally, what I would go ahead and do first is observe that that value is 1. P to the 0 power would be 1. And then that's supposed to be to the 5th power, which then you could write 1 times 1 times 1 times 1 times 1, which would have a value of 1. If you went ahead and multiplied those, you'd still get the same thing. P to the 0 power times 5, the 5th power. We'd get P to the 0 power there, which guess what that value is? 1. Let's say we had 2 to the negative third to the 5th power. We would still multiply the exponents because it's a power raised to another power. So that's to the negative third times 5. And we get 2 to the negative 15th. So if our directions say write it with a positive exponent, then we're going to flip that to the reciprocal. So we'll have 1 over 2 to the 15th power. And now it's a positive exponent. To find the power of a product, find the power of each factor and multiply some examples that we would have here. So it's kind of sort of like distributive property in a way. Now the tricky thing about these sometimes, let's say there's no exponent there, there's an understood 1. If there's not an exponent written, it's understood that there is at least a 1 exponent there. Okay, so we will have n to the first times the negative second, and same thing with m to the first times the negative second. And then over here we have n to the first times 2 times m to the first times 2 Alright, so then I've got to go work over here. So n to the negative second from this part right here, m to the negative second from this part. From here, n to the second, m to the second, all of that's being multiplied. And then I can start combining right here. Those two have the same bases and it's all multiplying, so I would do n to the negative second. They have the same base and it's being multiplied. And here we've got m to the negative second times m to the second, same base. So I'm going to add those exponents. Then I'll end up with n to the 0, m to the 0, and then each of those is 1. So then my final value on this, all that work for that measly, frustrating 1. Another example, and this one is one that frequently kind of trips students up, is let's say you had 2a, and a is to the 1/2 power, and 4. It's actually not the fraction that's the trouble. The part that students forget is that this 4 multiplies the exponent from the 2 and the exponent from the a. Now there is no exponent written on that 2, so we know that it's a 1 there. So 2 to the first to the 4th power, a to the 1/2 power to the 4th power, and then evaluate. We'll have 2 to the 4th times a to the 2nd. And you can evaluate 2 to the 4th, 2 times 2 times 2 times 2. That is 16, and 16a squared would be our final simplest form of this expression. All right, last example. To find the power of a quotient. Quotient is the answer to a division problem. Find the power of the numerator and the power of the denominator, and multiply. Okay, so it's very similar to the one that we just showed you. So look right here. See how this is a divided by b, and that is to the m power. And look what happens over here. The m is distributed to both your numerator and your denominator there, or your divisor and your dividend, whichever way you want to look at it. So if we had a and b being divided, and this is, let's put at least one exponent in here. Let's say b is to the 3rd power. And all of that to this negative 2nd power. So I'm actually going to take this negative 2 and multiply it, the exponents, to both the numerator and denominator, or divisor and dividend, however you look at it. So on a, the exponent is not written there, so we know it's a 1. 1 times the negative 2. Then on the bottom, we've got b to the 3rd. That gets raised to a negative 2nd. So then I evaluate both of those. This is a to the negative 2nd and b to the negative 6th. Now the fun thing about this one is that I've got negative exponents in both the numerator and the denominator. So the easiest thing to do is if it's negative here, if I send it across the fraction bar line, it's going to become a positive. Same thing here. This b to the negative sixth, if I send it across the fraction bar line, then my exponent, not the base, will become a positive. So look what happens here. We end up with b to the sixth over a to the second, or divided by a to the second, as our final answer here. And that's what we have for our exponent properties. Thanks for watching.